Hello and welcome to the Maths 2 component of the online BSc program on data science and programming. We have seen multivariable functions and today we are going to discuss limits for scalar valued multivariable functions. So, let us recall first that we have seen the notion of limits for sequences of real numbers. So, if an is a sequence of real numbers, we say that an has limit a if as n increases the numbers an come closer and closer to the number a. So, a sequence an is called convergent if it converges to some limit. So, that means there is some a such that an tends to a and that is an comes closer and closer to a. Here is a couple of examples. So, 1 by n summation 1 by I factorial n times sin 1 by n, and in a minute we will quickly recall what these limits are. A sequence n is called divergent if it is not convergent, and examples of such sequences are minus 1 to the power n, just n, and then log of 1 by n. So, in a minute we will see, we will recall what happens to these as well. And also we defined the notion of a subsequence. So, a subsequence of a sequence is a new sequence which we form by possibly excluding some entries of the original sequence. So, you choose only some of the entries of the original sequence. Okay. So, now the goal is to move from real numbers to higher dimensional space. So, R p, and in a minute we will talk about sequences there and convergence over there. So, let us recall first that what happens to these sequences. So, for these sequences 1 by n for example tends to 0, summation 1 by I factorial, if you remember this one, it tends to e, and then n times sin 1 by n, you can think of this as sin of 1 by n divided by 1 by n, and as n tends to infinity 1 by n tends to 0, and we know that sin x by x tends to 1. So, this tends to 1. So, this was one of the non-trivial limits that we actually computed in back when we did one variable calculus. Okay. And then we had these are divergent. Minus 1 to the power n is divergent because it keeps oscillating. So, minus 1 to the power 1 is minus 1, then squared is 1, then again minus 1 1. So, it keeps oscillating, it does not come close to any number. So, this just diverges because it oscillates. The number n diverges, but it diverges in a different way than minus 1 to the power n, because we say it diverges to infinity. So, what happens is it keeps increasing and it becomes larger and larger on the positive side, and it goes to infinity. So, we say that this diverges to infinity. And then similarly, if you take log of 1 by n, if you recall the log function, then this diverges to minus infinity. So, in one variable calculus we had these special things called infinity and minus infinity, and we had these sort of three different notions of divergence. One was just where it does not come close to anything, and the other two were where it diverges, but it diverges to infinity, and the third was where it diverges to minus infinity. Okay. So, now we are going to use this as the basis for exploring what happens in higher dimensional space. So, limits of sequences in R p. So, let a n tilde be a sequence in R p. Let us recall that we have been using tilde to emphasize when we are in higher dimension. So, a n tilde means it is a vector or an element of R p, and it has p components. So, there are p real numbers. So, those coordinates are denoted by a n 1, a n 2, a n p for each a n tilde. So, you have a sequence of such things, and for each one you have p many coordinates. So, you can look at the coordinate sequences in particular. So, for each coordinate, suppose I decide to fix the first coordinate. So, for the first coordinate I have a 1 1, then a 2 1, a 3 1, a 4 1, and so on. So, that is the first coordinate sequence. Then you have a second coordinate sequence, a 1 2, a 2 2, a 3 2, a 4 2, and so on, and then all the way up to the pth coordinate sequence. So, that is a 1 p, a 2 p, and so on. Okay. So, so we have such a sequence, and in the sequence consists of vectors or elements of R p, and each of those have p coordinates. That is the main thing you have to remember. And each of those coordinates forms a sequence in R in the sense that we studied on the previous slide. So, we say that a n has limit a tilde, which is some other vector or element of R p, where the coordinates are a 1, a 2, a p, if as n increases the sequence in the ith coordinate has limit a I. Okay. So, as I said, what you do is, let us say you take the first coordinate. So, from this sequence a n tilde, for each of these vectors you extract the first coordinate. So, then you get a 1 1, a 2 1, a 3 1 and so on. That forms a sequence in R, and you ask, does it have a limit? Well, if it has a limit, let us say suppose the limit is a 1. So, you keep that in store, then you go to the second one. You do a 2 1, sorry, a 1 2, a 2 2, a 3 2, a 4 2 and so on. Does that have a limit? Well, if that has a limit, you call that limit a 2, and then you go on. And you do this for all p coordinate sequences, and if all of them have limits, then you put that together into a vector which we have called a tilde, and then we say that this a n, which should have come with a tilde. So, a n tilde. So, we say that a n tilde has limit a tilde, which is this which has coordinates a 1, a 2, a p, if for each coordinate the sequence tends to the corresponding coordinate of a tilde. So, a n I, the sequence a n I tends to a I. Okay. So, basically the idea of convergence of sequences, so limits of sequences in R p is just borrowed from R. It's nothing very special. What you do is you look at each coordinate, ask if the sequence over there converges, and if it does converge, you put them all together. That's all that the limit in R p does. So, a sequence a n tilde in R p is called convergent if it converges to some limit. So, now beyond this, the definitions are exactly the same as we have for R. So, a sequence a n tilde in R p is called divergent if it is not convergent, and then we will define something called a subsequence of a sequence, which is given by deleting some terms. So, excluding some entries in that sequence, or you could take all of them, or you could delete some of them, exclude some of them. Okay. So, this is exactly in parallel with what happens in R, and in fact, to check limits in R p, you have to check limits in R. That is what this is saying. So, here is a couple of examples. So, the first example is 1 by n comma n times sine 1 by n. The second example is minus 1 to the power n comma n times sine 1 by n. The third example is a bit bigger. So, this is cosine n by n, some complicated looking expression, summation 1 by factorial, and then n times cosine of 1 by n. So, let us ask what happens to each of these and visualize the first two. So, the first sequence was 1 by n comma n times sine of 1 by n. So, let us see how this behaves. So, I am plotting this over the range of n as n goes from 1 to 500, and we will keep track of this point A. Yeah. So, when n is 1, this point is 1 comma 0.84. So, 1 because 1 by 1 is 1, and comma 1 times sine of 1 by 1. So, 1 times sine 1. So, this is 1 comma sine 1. So, sine 1 is 0.84. Okay, and as you increase n, you can see what is happening to this point. It started coming closer and closer and closer and closer to the point 0 comma 1, and this is at 156. It is already quite close, and you can see it is closing in further and further as we increase n. So, if we make this larger, so it is still not reached, but it is coming very close, and you can see it is moving and it is coming to 500, where it is almost at 0 comma 1. So, if we make it still larger, you can see it is not exactly at 0 comma 1, but yeah, it's very close. So, that says that as n tends to infinity, this sequence, so each coordinate, what we know what happens. So, for 1 by n tends to 0 as n tends to infinity. So, that is the first coordinate. So, that is why in the first coordinate we have 0, and in the second coordinate we have n times sine 1 by n, which we know because sin x by x as x tends to 0 tends to 1, we know that the second coordinate the sequence tends to 1. So, the limit is 0 comma 1 and we have seen a geometric explanation for that. So, for the second sequence we have minus 1 to the power n comma n times sin 1 by n. Now, we know from what we just did that minus 1 to the power n oscillates and n times sin 1 by n converges to 1. So, this function is this sequence is also going to oscillate. Let us see the behavior of this sequence. So, as it increases you can see that the point B is changing value from one side of the axis to the other, right. So, as I am at 1, this is minus 1 comma 0.84. When we increase it to 3, it is minus 1 comma 0.98. When we have n is even, say n is 8, this is 1 comma 1, and after that it just oscillates between minus 1 comma 1 and 1 comma 1. And so, we know that this sequence is not going to converge. It does not come close to any number in or rather any vector in R2. So, this sequence will not converge. So, if I play this on, you will see it is still oscillating between minus 1 comma 1 and 1 comma 1. And we knew that already, as I explained, because minus 1 to the power n oscillates. So, in other words, this does converge and this converges to 0 comma 1. We saw this graphically also. This does not converge, or this limit does not exist. And now we have the last one. Okay. So, let us look at these terms. So, the first term is cosine n by n. So, cosine n, as we know, varies between minus 1 and 1, and but when you divide it by n, so that means in absolute value it is between 0 and 1 by n, and then by sandwich we know that this tends to 0. The second one we have done in our previous video on limits, when we did limits for sequences. So, I will encourage you to solve it yourself, and if you do not remember, go back to that video and see what happens. So, it is 5 times something. I will leave that to you. The third one we saw in the previous slide goes to E, and what about the fourth one? So, the fourth one is n times cosine 1 by n, and unfortunately for this we know that cosine 1 by n, as n tends to infinity. So, 1 by n tends to 0. So, cosine 1 by n tends to cosine of 0, which is 1, but n shoots off to infinity. So, this is going to go to diverge to infinity. And so, what does this mean? That means that in this sequence as a whole, as a sequence in R4, 3 of these coordinate sequences do indeed have limits, but the fourth one does not. So, this limit also does not exist. Limit does not exist. Okay. So, I hope it is clear what we mean by sequences of limits in higher dimensions. So, we have to just check individual limits for each coordinate. Okay. So, let us now talk about the limit of a scalar valued multivariable function at a point. So, this is going to generalize what we saw earlier about one variable calculus, limits of functions of one variable at a point. So, let f be a scalar valued multivariable function defined on a domain D in R k, and A tilde be a point such that there exists a sequence in D which converges to A tilde. So, this is some technical condition that we need in order to define the notion of the limit. So, if there exists a real number L, remember this is a scalar valued function. So, f takes values in R, which means real numbers. So, if there exists a real number L such that f of A n tilde tends to L for all sequences A n tilde such that A n tilde tends to A tilde, then we say that the limit of A at A tilde exists and equals L. So, this is again direct generalization of what we have seen in one variable calculus. We denote this by limit x tends to A tilde, f of x tilde is equal to L. So, this is the same as saying that as x tilde comes closer and closer to the point A tilde, then f of x tilde eventually comes closer and closer to the number L. This is what it means for this limit to exist. And if there is no such number L, we say that the limit of f at a tilde does not exist. Let us do some basic examples. So, this first limit is a I to the power k. What is a I? A I is the ith coordinate of the vector a tilde. So, you look at that and raise it to the power k, right, and it is fairly obvious that that is what happens, because as x tilde tends to a tilde, you want x I to the power k. Well, x tilde tends to a tilde means x I is coming close to a I, that means x I to the power k is coming close to a I to the power k. Similarly, for the second one, you will get a I to the power k, because here we have assumed that a I is non-zero. So, even if your power is negative, meaning this k is negative, the same argument will hold. How about e to the power x I? Well, this will go to e to the power a I. How about log of x I? Well, again, if a I is positive, this is going to be log of a I, and then sine of x I will go to sine of a I. Please check this, whatever I am doing this fast, because I think this is very doable from what we have done before, but you should check this for yourself. It is very important that you check these and understand what is being said here based on the definitions in the previous slides. Fine. And then finally, if you have tan of x I and a I is between minus pi by 2 and pi by 2, then this is tan of a I. So, this is nothing very deep. It just follows from one variable calculus, and what I am going to try and tell you now is that most of the things that we do for easy limits are from one variable calculus. There are difficult limits, of course, and that's what we will be studying as we go along. Those need more refined techniques. Fine. So, let us look at some rules about limits of scalar valued multivariable functions. These are again in the same spirit as the ones for one variable calculus. So, if you have two functions such that for both of them the limits as x tilde tends to a tilde exist and equal f and g respectively, and you have some scalar c, then if you take c f plus g, then that limit is c times capital F plus capital G. So, you can push the limit inside and take the scalar out, that is what it says. And of course, special cases of this are where c is equal to 1. So, in that case it will say that the sum of the limits is the limit of the sums. Similarly, you can take c is minus 1, and that will say that if you take the difference of the functions and take the limit, that is just taking the difference of the limits. You can just take the function g is 0, and in that case this is saying c times f limit, you can take the c out. Okay. So, the next one is for products. So, if you take the multiplication of two scalar valued functions, and this makes sense because these are scalar valued multivariable functions. Then if you take the limit and both of these limits exist as x tilde tends to a tilde, then the limit is just the product. So, it is f times g. Similarly, if you take the quotient f by g, here of course, you need the caveat that as x tilde comes close to a tilde, the limit is non-zero. So, this capital G is non-zero. So, once that happens, the quotient also has limit and it is exactly capital F by G. Okay, so, let us quickly write down what this means based on what we have seen. So, for example, if I have a function like this. So, if I have h of x y z is x square y cube plus y cube z squared plus e to the x, right. Let us say e to the x y z. Okay. And I want to ask what is the limit of let us say x y z tends to 1, 2, 3 of h. Well, let's see if I can apply whatever I have above. Okay, let me not take e to the power x y z, instead let me take just x y z. We will come to e to the power x y z in a minute. So, if you take this limit, well, first let us look at x square y cube. Okay. We saw on the previous slide that both of these individually exist, and this limit is going to be 1 squared, just substitution, and this limit is going to be 2 cubed, right. Then you can use the second one and say that for x square y cube, the limit is 1 squared times 2 cube. Okay. Similarly, for y cube x squared, it will be 2 cube times 3 squared, and for the third term it will be 1 times 2 times 3 using 2, and then using 1, that you can, the limit of a sum of functions is the sum of the limits if all of them exist. You can just say that this is limit of each of these individually, and of course, limit x y z tends to 1 2 3, x y z tends to 1 2 3, x y z tends to 1 2 3, and we have computed all those using again these rules. So, this is 1 squared times 2 cube plus 2 cube times 3 squared plus 1 times 2 times 3. Essentially, what we have got is you can just substitute h of 1 2 3 inside this function. So, you can, this limit is exactly h of 1 2 3, which is so 8 plus 8 times 9 72 plus 6. So, whatever that is I think 86. Okay. So, I hope it's clear how these rules are useful. Okay. Similarly, you could have something like limit, let us say x by y as x comma y tends to 1 comma 1, then that would be just 1, because you can substitute for the numerator, substitute for the denominator, and for the denominator it works because the limit is non-zero. Okay. So, this is very similar to what we have done in one variable calculus. In many places you can just substitute the values. Okay. Not always though. Remember, even in one variable calculus we had trouble with substitution, for example, in things like sin x by x. Okay. But I hope it is clear how these rules can be used. So, for polynomials, for example, it is very easy to find limits. Fine. The next thing that we want to study is composition. So, suppose f is a scalar valued multivariable function and g is a function of one variable such that the composition g composed f is well defined. Then, if limit f of x is f and limit g of x is L, then limit g composed f of x is also L. Okay, this may take a little time to digest. What we are saying is this. So, suppose I have the function h of x y z is e to the power x y z. Then I can write this function as a composition of two functions. One is h of x y z is x y z. This is a very nice function that we understand, sorry, not h, but f of x y z, and the other function is, let us say, g of u is equal to e to the power u, again a very nice function. Both of these are nice functions. Let us see what happens to limit. Let us say I want to compute limit x y z. So, want limit x y z tends to 1 2 3 h of x y z. Okay, this is what I want. Okay. Now, whatever we did on the previous page does not unfortunately help us directly, but what we can do is we can use the fact that this is a composition. So, let us first ask what happens to f. Well, this of course we know what happens. This is 1 times 2 times 3. So, in terms of what is here, this is capital F, and yeah, and then if we have limit x tends to f of g of x. So, here we want u tends to this number, which is 6. So, u tends to 6 g of u, which is e to the power u, this is e to the power 6. So, what is the net result? The net result is that this limit that we wanted is exactly this number here, e to the power 6, because I can compose, right. Okay, so, that is the answer, and this is again essentially what we are saying is you can substitute. So, this is a useful rule, when we have functions beyond just polynomials. For polynomials, the previous page whatever we had, or rational functions, the previous page sufficed. But if you have exponentials, trigonometric functions, logarithms, then we can use this composition rule and we can find the limits. Okay. And finally, we have the sandwich principle, which again we have studied in one variable calculus. So, if you have two functions f and g such that for both of them the limit as x tends to a, x tilde tends to a tilde is L, and then if you have some function which is caught between them, sandwiched between them, then the limit as x tends to a tilde, h of x tilde is also equal to L. So, you will see an example of this in the tutorial. So, I will not expound more on this, but we have seen examples already in one variable calculus. Fine. So, let us come to finding limits by substitution, and this is where you have to be fairly careful. So, suppose we want to find the value of the limit of a function f of x at the point a tilde. So, that is limit x tilde tends to a tilde f of x tilde. So, often we can substitute the value of a tilde in the expression of f of x tilde and obtain the limit. This is what many of the examples that we have seen we could do. So, unfortunately, this does not work when the function gets slightly complicated, or the point a tilde does not belong to the domain of the definition of f of x tilde, right. It may happen that f is not defined at a tilde at all, then what do you do? So, let us look at this example. You may actually remember this example from somewhere else. In any case, let us try and understand what is limit x tilde tends to 0 0 x cube minus y squared x by x squared plus y squared squared. So, what we want to ask is what happens as to this limit as x tilde comes close to 0 0, which means x y comes close to 0 0. Now, we can't use any of the previous things, because if you look at this expression, it is a 0 by 0 type expression. So, you can't, so the rational function where you had f by g, unfortunately the denominator here is becoming 0 in the limit. So, you can't use that rule. So, there is no other rule that we can really use. So, how do I try to attempt this? So, we have to sort of try and do this by first principles. Ahead we will also see other ways. So, we will try and look at what happens to sequences as they come close to 0 0. So, let us first try and look at sequences of the form. Let us say I look at a sequence of the form a n tilde is equal to 1 by n comma 0. Okay. So, along the x axis as I come close to this point 0 0, what happens to this function? So, if you look at f of a n tilde, well, I can substitute 1 by n comma 0 in this expression, and what do I get? So, the numerator is 1 by n cubed minus 0 squared times 1 by n, and the denominator is 1 by n squared plus 0 squared the whole squared. So, this is, if we compute this, this is 1 by n cubed divided by 1 by n to the power 4, which is just n, right. And what that means is, if you take f of a n tilde, that is exactly n. So, f of a n tilde as n increases diverges to infinity, right. So, this function in terms of what we have seen, there is a sequence for which this function diverges to infinity. Just for so in particular what this means is that the sequence does not have a limit. So, this limit x tilde tends to 0 0 does not exist of this function. Okay. Let us just for practice take another sequence. So, 0 comma 1 by n. So, let us look at what is f of b n tilde. So, f of b n tilde, if we substitute that, so the numerator is 0 cubed minus 1 by n squared times 0. So, that is 0, and the denominator is 0 squared plus 1 by n squared squared. So, which is 0 by something non-zero, which is just 0. Okay. So, for this sequence b n tilde, f of b n tilde does actually have a limit. So, along the y axis this function does have a limit. So, notice what is happening here. Along the x axis, as we take a sequence along the x axis, which was 1 by n comma 0, the f of a n tilde diverged to infinity. Along the y axis, as we took a sequence, that actually converged to 0. So, we have two sequences which are giving us two different limits. So, there is no way, in fact, one of them diverges. So, this limit does not exist. Okay. So, the main point is you cannot substitute. Okay. This, for example, in this kind of function, you cannot substitute, and this limit actually does not exist. So, this idea of taking sequences from different directions is very important, and we will see more about this ahead. Thank you.